So, as a part of discussing about the memory that we find inside our general purpose digital computers, we are going to today talk about, we're going to today brush up our knowledge of, we were talking about memory hierarchy. We will be talking about that as it is linked to various different types of software, etc. And we will be brushing up about how the program is run. We'll be also, I think, today, if we have the time also, we'll be talking about the basics of how, in general, the memory categories are defined and not defined, rather, how they are described, how they sort of differ from each other. We have already seen. But what we're going to do today is that how they're used, we're going to talk about the basics of that. I'm going to also talk about how we use this in case of software. So, first of all, let us go back to the uh, diagram that we were using in the last class. So let us just go back to that first. So this is the diagram. Now you see, as you can very well see, that we were talking about this hierarchy, that this time, or this side rather, not this side, it is cheaper and bigger, but it is also slower. Whereas this side, it is costlier and smaller, but it is also faster. The reason we do not use a large memory like the secondary storage that we have seen here, this is actually the general symbol of a secondary storage. This may be a hard disk, and this may be an optical drive, magnetic tape, something like that. Although I must reckon that magnetic tapes and others are very few and far between. We are talking about ID drives and SATA drives and others, and we're talking about solid state devices. These days they use solid state devices. So whatever device that is, why don't we use this as the main memory? Well, because the access times are very high. The access times are very high, and generally the secondary storage that we see here, they are permanent memory, so that we can store stuff there so that it remains there. And here, as you can see, those mainly or mostly are serial access devices. For example, a box standard ID device or SATA drive, it will be a serial access device where the read write head, it is the logical diagram is like this. There is a read write head. By that we mean a point where we are reading and writing from, and the device moves against that. So when we read something or write something, the device must move against the head to affect a read or write. Or it will be like this, like a tape basically. From end to end, there are several data arranged in various locations, and wherever we are currently with the read write head, the read write head moves left or right to find that particular position. And in case of random access memories, okay, I'm not just talking about RAM. Random access memories can also be, for example, the uh, solid state devices, solid state hard drives are also somewhat, or part of it at least, a random access, if not all of it, but they're there. So with those, the logical view is like this, that there are all these locations come with a separate read write head, and so that whenever we want to read from a location or write to it, the read write head directly reads from it or writes from it. It's a direct access. Whenever we want, we can go there and we can get the data from there. Not like this where it has to move and then we can find the data, but we just have to find the proper head for the proper location and then we can use it. So, in case of a semiconductor memories, like say for example the RAM, okay, the logical view, where this logical view can be further detailed into another logical view, which we have seen before also, that there is a memory here, which is this M. and these two lines, thick lines, are the buffers. These are the input buffers and the output buffers. And what happens here is that some sort of address bus, which is a series of lines that carry data, that is a bus. Address bus carries the digital pattern that represent a number which corresponds to a location in memory, and this location is the address. So that means it carries the address. So the address bus carries the address, and from there the particular location in memory is located, and it is selected through various different types of digital logic. It gets selected, and then a read or write signal will indicate whether they want to read or write. And then what will happen? Well, then what will happen is, and how does it happen? The address comes into the address decoder. As you know, or as you may very well know, that the decoder is a device which takes in a bit pattern and gives out a pattern which contains one, and basically the others are zero. So basically, from a series of zeros and ones, it produces an output with a corresponding one and several others. It can be, for example, if it's an 8-bit device, it can be 0, 1, and all the other zeros. There can be 0, 0, and then 1, and something like that. Okay, corresponding to the device, it happens like that. Now, when uh, it selects it and the read or write signal says whether it is going to be reading or writing, correspondingly, for read, output buffer is opened, input buffer remains closed. For write, output buffer remains closed, input buffer is opened, but opened where? Well, it is already selected there. So if you write to it, it writes there. If you read from it, it reads from there. So this is how this. So as the address, as far as the address or addressing goes, obviously we can choose any particular address on this memory. Any particular address can be chosen just as we wish or just as we would require. Any particular address can be chosen, and so it basically mimics a logical diagram like this, where we would imagine that all the locations, it is as if, so what we're doing is we are selecting this any particular place we're selecting, and then we are writing or reading to it. So it is as if all of these memory locations are having a single head each. This is a logical diagram. Obviously, it's not a physical manifestation. It's a logical diagram. It means that it looks like each of these location has a single read write head from which you read or write. Okay, so that is the thing. Now, then what happens is that normally data that resides here, okay, so this side obviously is the secondary storage is normally permanent storage. Okay, so this is normally permanent storage, and these are normally temporary storage. Okay, and this is permanent. Now, why these are temporary and why this is permanent is very simple. Well, these ones, we hold the data in latches and registers. Okay, latches and registers and flip-flops. Now you see, when the power is turned off, automatically those transistors, you cannot read or write from them, and they basically go into well, the power in them is off, so the data inside them, that is also lost. That is why these are all permanent storages. But because these are made out of digital logic, and they are faster to access. Okay, and these provide the intermediary positions where the data can be kept so that the computer can use them. Now, just as I have told you how this is temporary, there must be something in the computer which holds the data permanently. Let me give you an example. Operating system. Whenever you are turning on the computer, the operating system must come on. So that means that operating system you're not loading. So where does it go? When you're talking about BIOS, So basic input output service. Okay. So where does it go? So BIOS basically is a firmware. Operating system is a type of a, well, we can say that it is a type of a system software, although uh, it is partly system software because not all parts of the operating system are actually dealing with the hardware. What is the system software? System software, as you may know from beforehand or from software engineering, system software is the software that handles the hardware of a computer directly. Now, in this case, we may not have that luxury that the operating system will, all parts of it, rather, it is not required, not just the luxury, it is not required for the operating system, all parts of the operating system to access the computer's hardware. Not at all. So, all of it is not system software. But, for example, the operating system kernel, this is basically a system software. The kernel is the lowest part of the operating system that sits directly above the hardware and makes the hardware do. Anyways, this is not a part of this course. This BIOS is there, basic input output service. What does it do? It boots the computer. It does something called post powered on self test, and then it boots the computer by loading the operating system. Now you can imagine these and also all other compute or all other programs. For example, if you write a program in C, where does it go? Obviously, you store it in the computer so that you can use it later on, isn't it? But then if you stored it in RAM or if you stored it in any other part of volatile memory, so if we can just flip our page to this, if you store it in anywhere here, what will happen? It will be lost. This is the same thing that happens if you, for example, are actually working with Turbo C++ and you have not saved your buffer. If the computer is turned off, you do not get your program back. Is it not? The reason because the reason for that is because you have actually stored it in volatile memory. Well, when you are working, this is working memory. So whatever you are writing is getting written here. What you see on screen is getting written here. But because you have not saved it, immediately after you switch off the power in the transistors are lost. And so basically your entire data is also lost. When you press save, then a suitable location is found out in this part in the secondary storage, and the file gets written on the secondary storage medium, and its location is noted in the file allocation table. You've heard of that, all of you? Okay, so its location is getting written in, or gets written in the file allocation table. So when you need to find your file, looks up the file allocation table, computes the see, file allocation table isn't just simply a table. There are lots of different algorithms for calculating, because any table will take up a lot of space. So you want to reduce the space as much as you can. So there are lots of calculations to be done. Through these calculations, the location of a file is located. If you had to store, because there are so many files, if you had to store one address for each file without any calculation, if you just have to tabulate it, the table would be huge. So instead of that, some sort of mechanism is affected, so that you can just do some addition and subtraction or whatever, do some offsetting, and you can find the file on the hard disk. But anyways, nevertheless, if you can just view it as a simple table also, this is a table of locations for the files. So it gets stored in this secondary storage medium. After you press save, only then, just to mention, because you are also doing data structures in Turbo C++, I guess, just to mention that if you are writing your program, it is in RAM. Now, if you press F2 in Turbo C++ IDE, only then does it get stored. As soon as you write something in RAM which has not been stored in the location of the file on hard disk, you will see that at the bottom right corner, bottom left corner, a star appears. That means it is an unsaved buffer. So you must save it, otherwise if the power goes, all of it goes. Now, this is the, so all of these need to be stored in the, then it is clear that all of it needs to be stored in the secondary storage medium. So because it is secondary storage, I mean, it is called secondary storage, we call it secondary storage. Actually, it's permanent storage. That's what it is, because it's slow and cannot be used for the work, cannot be used to work all the time. Maybe we cannot use it as a main memory. It's called secondary storage, and the other ones are primary storage. But this is also permanent storage. So we use some sort of physical embodiment of data, or we use refresher circuits to keep the transistors charged when the power is off. So here example is ferro magnetic materials and optical medium. Okay, ferromagnetic materials like tapes, like hard disks, optical medium like CD-ROMs, etc., or refresher circuits. Okay, like for example, you have a ROM inside a computer. Okay, now there are several different types of ROMs which we'll discuss in a bit, but there are these ROMs, read-only memories, and obviously then there are the flash drives that we use as pen drives, for example. These are, ROM is internal, these are external. Also solid state devices that we discussed a while ago, or just a moment ago in fact, also solid state storage. Thereby we have a situation where uh, there are some of it. Okay, so obviously, as you can imagine, before we say what we have a situation as, let us just say, let us just first sort this out. This is obviously cheaper. This is obviously cheaper. Because why is this cheaper? Simply because you just, for example, if you are writing, what used to happen in case of tapes? What used to happen in case of audio tapes, spool tapes of our grandfather's time or our father's time? What used to happen? There used to be a tape. So it was, the scheme was like this, that there used to be a tape with magnetic material on it. So let us say this is magnetic material. Okay, and there's this read-write heads are there, either read-write head or heads, whatever the arrangement is. Now these change the polarity of the magnetic units here. They have rectangle hysteresis cores. They change the polarity of these have spins basically. So it's either a right hand, these change it to a right hand spin for a 1 or a left hand spin for a 0, like that. It is because of the magnetic field that they change their spin. So this is how the magnetic materials are done. So there's a huge tape, strong but not very expensive. Coat it with ferromagnetic material and use the electronics, electronic mechanisms to store the data and read the data. So as a result of this, not very expensive. But as a result of this, also very slow, because it has to revolve around and the addressing is serial and so on and so forth. Very slow. After all, RAMs, etc., which are working with latches and registers, they are working at the speed of electricity, electric signals. And this is actually mechanical in nature, so obviously this is going to be slower, much, much slower. Another one was the optical devices. What is there? These are grooves, zeros and ones, zeros and ones. And there is a laser that falls on it. As this goes around, or as it is dragged along, normally it is not dragged along. We're talking about a CD-ROM or a DVD-ROM. So basically, it's a disk and it goes around, and the laser is there. Okay. As this goes around, and it is divided into, obviously, as you know, tracks and sectors. So these are tracks and these are sectors. These are sectors, these are tracks. The round ones are tracks and these are sectors. As it goes around, the laser bounces off the surface. So there is obviously a matter of timing here also. If it bounces off there, it doesn't mean anything. It has to bounce off there. So whether it's a 0 or a 1, it has to be written in proper intervals of time. So how do you interval the laser? Very simple. Timing. Now when the laser is engraving something according to timing, so it's like this: engrave, stop, engrave, stop, engrave, stop, engrave, stop, engrave, stop, engrave, stop, like that. And this engrave stop is obviously this pulse is provided by the clock. Now, when you are engraving this, according to the signal, you're either engraving a 0, or you're either engraving a 0 or a 1 or a 0 or a 1 or say a 1 or a 0, like that you are engraving. Your laser pulse is engraving this. Now, I have drawn it like this. It may be some other pattern, but it is like this. Basically, the pattern is engraved. Now, when the CD-ROM is again used for reading, the laser goes read, stop, read, stop, read, stop, read, stop, read, stop, read, stop. According to the clock, it reads, stops, reads, stops, reads, stops. And when it reads, what happens is again the laser, now this time it is a reading laser. So the beam is not to engrave, but to read. So it is only used to bounce off. So basically the laser is now there to just come and bounce off the surface. Now when it bounces off this particular surface, it can understand that it is a large groove or a small groove. And by the nature of the bounce, the laser or the reader can understand whether it's a 0 or a 1. It depends upon how the laser pulse is bounced back. That tells the electronics whether it's a 0 or a 1. Now, so these are the two normal technologies. There are several others as well, very much like this. In the very olden days, they used to have paper tapes. We are not going into that. If you want to discuss about paper tapes, you can find them on the net. But we're not going into that because they're not used for a very long time. No point in discussing them here. So this is how the magnetic materials, or this is optical material, how these work. So very cheap. On the other hand, when it comes to the second type where refresher circuits are used, what I mean by that is, let us say these are the data all arranged one after the other, and is a semiconductor memory. Now, as long as power is in, as long as power is in, Okay, so basically these are active, these are holding the data, and this can be read or write, read from or written to. Okay, this can be read from or written to. However, when the power is switched off, this this blanks out. So you cannot read anything. Very simple. So what do you do? So if you have to have some sort of device which stores it electronically, then what do you do? Simply, you have to couple it with another refresher circuit. This is a very simple mechanism. I'm just giving you the logical diagram. Obviously, I'm not giving you any physical implementation. That is up to the company, up to the designer. It is a logical diagram. The only purpose of this is whenever this goes blank, okay, this refreshes it. So there is a copy of this here. There. So it's a copy of it here. So if this is main data, if we call this as main data, this is a copy of main data, and this is internal power source. For example, the BIOS battery. Now, how many of you know about the BIOS battery or the ROM battery? Do you know, all of you? When the motherboard is open, there is a battery which is like a button battery, a like a big small coin. Do you know? Well, next time you open the computer, next time, you just you can look it up. So it's like that. It's an internal power source. Now, what does it do? Very simple. It keeps this refreshed. That's all. It keeps this refreshed. That's all. So when this is gone, this may be gone because of several things. So main data erased due to what we called destructive read. That means when you read it, the data is destroyed or power off. Okay, what does that mean? Refresher rewrites data. So when the power is turned off, as I said, main data erased due to destructive reads or power off. The refresher circuit will keep these things charged up. This will keep it charged up with the data. So when you are turning on the power again, the data is not lost. So when you are turning on the power again, the data is not lost. You must say, sir, why don't we connect this directly to the power? That would save us having the refresher circuit. Well, no, not really, because you see, destructive read would have erased the data. What is destructive read? As I said, there are certain types of read in certain devices we have destructive read. What is that? When you read the data is erased. The transistors are taken to some random state. Destructive read can also be found in some sorts of um, physical storage devices as well, like I mean mechanical storage devices like ferromagnetic devices as well, where when you read it, it actually destroys the data in there. It is that kind of an arrangement. So for all of these, you need a refresher circuit. The refresher circuit is the backup. So whenever the data is erased, like when the power is off or when a read happens, the data here is rewritten in the corresponding data in the main data area from the copy. And this copy is actually kept charged up. This copy is actually kept charged up. This is the basic mechanism by which ROMs work. And also other devices, okay, like for example, uh, I mean any device that is storing data electronically but want to store it permanently. That means even after the main power is cut off or there is a power cut or the computer is shut down, so the main power is cut off, the data must remain in there. If something like this happens and it is not a medium like an optical medium or a magnetic material like a physical storage sort of a thing, although it's a misnomer, this has also got a physical existence. So I don't know whether it is right to call this physical storage and this is not physical storage, not like that, but I'm saying that if this is being stored with digital logic, this is not being stored with digital logic, this is just done by engraving, sort of a changing magnetic poles, engraving like that. But this is not any kind of engraving or changing magnetic poles. This is actually um, the we are sort of using transistors. That means we are using latches, registers, and flip flops to actually store the data. But we need to have that data even after the power is turned off. So we need to have the refreshing mechanism. So with this, we stop our lectures today. It's time for your break and your next lecture.